Archimedes is credited with discovering the principle of buoyancy. The principle is easily explained for any fluid, gaseous or liquid. In equilibrium, consider a portion of fluid defined by the imaginary closed surface as illustrated by the irregular dashed boundary in the picture here. If the body of the fluid could be sucked out from within the closed cavity and replaced simultaneously by the forces which is exerted on the boundary of the cavity as shown in the picture here B, the equilibrium of surrounding fluid would not be distributed. Furthermore, a free body diagram of the fluid portion before removal, shown in the part C, shows that the resultant of the pressure force distributed over its surface must be equal and opposite to its weight mg and must pass through the center of mass of fluid element. If we replace the fluid element by a body of same dimensions, the surface force acting on the body held in this position will be identical to those acting on the fluid. Thus, the resultant force exerted on the surface of an object immersed in a fluid is equal and opposite to the weight of fluid displaced and passes through the center of mass of displacement fluid. This resultant fluid is called the force of buoyancy. So we can add definition: the resultant force exerted on the surface of an object immersed in a fluid is equal and opposite to the weight of fluid displacement and passes through the center of mass of the displaced fluid. This resultant force is called the force of buoyancy. F where rho is the density of the fluid, g is the acceleration due to gravity, v is the volume of fluid displacement. Rho density of the fluid, gravitational acceleration, and v volume of fluid displacement. In the case of liquid whose density is constant, the center of mass of displaced liquid coincides with the centroid of the displaced volume. In the case of the surface boundary between a liquid and gas, such as water and air, the effect of gas pressure on that portion of the floating object above the liquid is balanced by the added pressure in the liquid due to the action of the gas on its surface. An important problem involving buoyancy is the determination of the stability of a floating subject. Stability of floating objects. Such as a ship hull shown in the cross section in an upright position in the figure shown here. Point B is the centroid of the displaced volume and is called the center of buoyancy. Point B, center of buoyancy. The result of the force exerted on the hull by the water pressure is the buoyancy force F, which passed through P. F, buoyancy force, rho g v, if the ship is caused to release through an angle alpha, this picture, the shape of the displacement volume change and the center of buoyancy shifts to B prime. This point. Center of buoyancy after release through an angle alpha. The point of intersection of the vertical line through B' with the center of the ship is called the meta center. M is point meta center. The point at the cross intersection of B and B prime, and the distant edge of M from the center of mass G is called the meta-centric height. For mass, hull shape H remains practically constant for angle of least up to the above 20 degree. When M is above G as shown, there is a rightening movement which tends to bring the ship back to its upright position. So if M is above G, stable, and if M below G, unstable case. This is the end of this section and the end of this chapter.